Hello and welcome to lesson 9.4 on partial fraction decomposition. This is the lesson that I taught in class. This was not one of our online videos to watch, but in case you were absent or in case you just want to look at it again, here it is. This is what we covered. So, partial fraction decomposition is our topic. And this is a topic that's kind of covered in Algebra 2. Sometimes it's covered in pre-cal. It kind of depends on your teacher. At Cedar Ridge, our pre-cal teachers cover this again. Sometimes it's just in Algebra 2, and then it comes back in calculus. So you're probably going to see it 3 times if you're at Cedar Ridge, once now, then again next year in pre-cal, and then again once you are taking calculus. Okay? The end goal is to use this for calculus. And what partial fraction decomposition is taking a complicated fraction, right? For instance, this guy right down here, right? And decomposing that fraction, decomposition, right? Decompose, meaning splitting it into smaller fractions, which we call partial fractions. So each of those is a partial fraction. And that is because these fractions are a part of what adds up to get your answer here, right? Whatever your original rational expression was. So it's splitting it apart. And that's decomposition, okay? Now, as far as algebra goes, are we going to use this to really accomplish anything, to solve any problems? No, actually we're not. This is simply an algebraic technique that is very useful for calculus. I actually remember when I was in college, I took differential equations. We call that diff-EQ. Differential equations, which is it's a math class that comes after calculus, specifically looking at differential equations. It's something you learn about in calculus. And I remember the professor using this partial fraction technique, and a bunch of hands went up and saying, "Professor, what are you doing? What's happening? How did you do that? What's going on?" And he said, "Oh boy, if you don't know this, well, I suggest you go home and figure it out," because this was something he just expected you to know coming in. And a lot of people seem to not remember it. But that was just my experience, okay? I don't know how other people in differential equations have gone, but, you know, it might be something you forget. But I remembered it, and I remembered it well, so it was nice to be in the group of people that knew what was going on. Okay, so there are different patterns of decomposition we're going to talk about. However, all we're covering here in this video, Algebra 2, is linear factors and repeated linear factors, okay? The rest is pre-cal or calculus, okay? Calculus. I don't know how hard your pre-cal teacher is going to get with these, but you'll certainly reach max difficulty with calculus, okay? So there you go. But we're only covering these first 2, linear factors and repeated linear factors. When we say a linear factor is just like, let's say, I don't know, I have blah, blah, blah up top, x plus 1 and x minus 3. X plus 1, that is a linear factor, right? It's a factor because it's in factored form, and the term is linear because the degree is 1, right? So both of these, x plus 1 and x minus 3, they are linear factors. Quadratic factors look like this. Let's say I got x squared minus 7, and then x plus 1, right? X squared minus 7, that's your quadratic factor. X plus 1, that's your linear factor. Yeah? And then sometimes, you can keep going. You don't have to just stop at quadratics. You can do cubics and so forth. And there's a specific rule or pattern to learn with those. And then the last one is improper fractions, which by definition is when the numerator is more than the denominator, right? So like 17/5 is an improper fraction. Or algebraically, that's when the degree of the numerator is equal to or more than the denominator. So when you have x cubed plus blah, blah, blah over x plus blah, 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 that would be an instance where you have to use improper fraction technique to solve. And it's actually not that bad because all it is long division, and then it jumps back to the previous stuff. But anyway, that's just an overview of partial fractions. Let's actually get into this and talk about what we're doing. Now, there are two methods I'm going to discuss in this video for partial fraction decomposition. Two methods. The first is zeroing out each factor. We're going to talk about what that means when we get to it, but it's essentially thinking about numbers or values for x that make a factor go to 0, using that to sort of eliminate unknown variables and then solve the equation. This is Mr. Spake's go-to method, so I actually prefer method 1 over method 2. And method 2 is using systems of equations. And this method, method 2, is kind of the more textbook method. I've actually never been taught partial fractions in college. I only ever learned it in high school. But I don't know. Some college professors might use this method, using systems of equations. It's more textbook, okay? And it is useful over method 1 for one reason. More useful than method 1 when given harder problems. And by harder problems, I mean a lot of unknowns. Okay, so a lot of unknowns. Okay, so we're going to be, in our practice, we're only going to be looking for one or like 2 or 3 unknowns, like A, B, and C. But right now, that's just simple. That's just 3 unknowns. You can get A, B, C, D, E, F, and G, and H even, maybe, really. And you just keep on going, really. You could have 6 unknowns. And the more unknowns you have, the harder the method 1 is going to be. So you may enjoy method 1 right off the bat more than you like method 2. However, know that method 2 is a very useful strategy for more complicated problems, okay? It's also really nice if you have access to a calculator. If you don't have a calculator, I might say this. More useful if you don't have a calculator, okay? Because the systems can get really complicated. And so if you don't have a calculator, you might want to do method 1. And you can actually use a combination of method 1 and 2, as you'll find as you work through these. Okay, let's go. Let's do this. Enough talking, Mr. Spake. Let's actually talk about this. So example 1, linear factors, method 1, zeroing out. Now, we need to split this fraction up into partial fractions, which means it's going to be fraction 1 plus fraction 2 plus fraction 3 plus fraction 4. Well, actually, how do we know how many fractions we have, right? How do we know? Well, begin by factoring out the denominator. Okay, so I'll say step 1, factor denominator. Okay, so here's step 1. I say 3x plus 5, and then we're going to factor the denominator. Let's see, 2x and x. Looks like we want minus 3 plus 1. Is that right? Yes. Okay, so that is how the denominator factors. Okay, that is step 1. Now step 2. Create partial fractions. Now, for linear factors, if I want to split this up into fractions, of things, right? So blah, 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 blah. If I want to split this into multiple fractions, look at your denominator. You know that the least common denominator here, this denominator has two factors, 2x plus 1 and x minus 3. So naturally, what's going to happen is this is going to have a denominator 2x plus 1, and I'm going to have a denominator x minus 3. Because if you think about adding the fractions together, well, one of the fractions has to have 2x plus 1 as a factor. The other fraction has to have x minus 3 as a factor. Okay? And so there it is. Those are our partial fractions. The thing is, we just don't know what's in top, right? And since we don't know what's up at top, we'll give them names. We'll call it A and B. It's pretty standard to use these letters, A and B, because they are constants, not variables. They're unknown constants that we want to look for. Okay, so that's step 2. Okay, I should have written some more space. Let's say step 3. Step 3 is to multiply by your LCD. And this is to cancel all denominators. So I'm kind of slow writing this out. Step 3, if you multiply by the LCD, then on both sides, then you will effectively cancel all denominators. And then we can do something with this. Okay? So let's take let's say we'll do this as step 3. So we're going to take 3x plus 5 over, oh my God. You know, I don't want to rewrite it, actually. Look, you're taking this entire thing and multiplying by the LCD, which is 2x plus 1 times x minus 3, right? You see, that's the least common denominator because, well, this one has both factors. This has one of them, this has the other. So I multiply by the LCD to get rid of all denominators. Now, you have to do a little bit of forward thinking here. You could put this in every one of these numerators if you want, but really it's easier to just think about what's going to cancel. Take this denominator, and we're multiplying this on top. Then 2x plus 1 and 2x plus 1 cancel, and x minus 3 and x minus 3 cancel. So we are left with 3x plus 5 equals, and by the way, this is step 3. Now take a look at this one and multiply by this, right? Your denominator is 2x plus 1, and if you compare it with the LCD, you put 2x plus 1 on top. The 2x plus 1s cancel, but I'm still left with x minus 3. So there's going to be an x minus 3 up here, okay? Which means this is a times x minus 3. And now I'll move to the next one. Same idea. Taking this, multiplying by this on top. The x minus 3's cancel, and I have 2x plus 1 on top. So this is plus b times 2x plus 1. And finally, step 4 is going to be step 4. It's essentially just plug values of x in. Or I'll say 0 out each factor. Yikes. I cannot type or draw factor. Okay? Okay, let's do this. So what do I mean by zeroing out each factor, right? Well, take a look at this term right here, a times x minus 3. If x is 3, then I get a times 3 minus 3, and that makes this factor right here equal to 0. And then this would be a times 0, so it would be gone. So the 0 of that factor is 3. So if I say x equals 3, right? If I plug this into the equation, 3 times 3 plus 5, that's coming up from here, right? Equals a times 3 minus 3 plus b times 2 times 3 plus 1. Notice what happens. 3 times 3 is 9 plus 5 is 14 equals, well, this is 0, so it's crossed out. And then it's b times, well, 2 times 3 is 6 plus 1 equals 7. So that's b times 7. Therefore, if you divide both sides by 7, right, you'll get b equals 2. So I'm going to write, therefore, b equals 2. And you found b. So you see what we did is we used a careful choice for x, saying x equals 3, plug that into the equation, evaluate it, that effectively eliminates a from the equation and creates a single equation with just one unknown, which is b, and then we can solve. So now just think, okay, let's look at the other linear factor, 2x plus 1. What would you make in for x to cancel this term, right? To zero it out. Think about it. If you need to pause the video, give it some thought. Think about it. Here's the answer. X equals negative 1/2. If you choose x equals negative 1/2, then I get 3 times negative 1/2 plus 5 equals a times negative 1/2 minus 3 plus b times 2 times negative 1/2 plus 1. But you see that is effectively 0, so we cross it out. Now you can evaluate the rest of this. This is like negative 3/2 plus 5. And this is a times negative 1/2 minus, let's call that 6/2, so we can combine those. And while we're at it, 5 is actually 10/2. So then negative 3/2 plus 10/2 is 7/2 equals a times, this is negative 7/2. Yeah? So you ask yourself, negative 7/2 times some number a equals positive 7/2. Well, that number a should be negative 1. Okay? And so there you have it. And so now that you found b is 2 and a is 1, negative 1, plug those back into your decomposition. So I'll say the final answer. Right, final answer. 3x plus 5 over 2x squared minus 5x minus 3. This decomposes into a over 2x plus 1. That's negative 1 over 2x plus 1. And if you're saying, where's Mr. Spate getting that? I'm getting it from up here and plugging in negative 1 up here. Okay? Plus, b is 2 over x minus 3. And again, if you're wondering, b is 2, and it's this term, b over x minus 3. And that is the decomposition. Okay? That is simply splitting your rational expression into two simpler rational expressions, partial fractions. Okay? And that's method 1. Hope you like that. I like it. I like this a lot. I think this is fun. Okay? And that is the zeroing out method. Okay. Let's move on. Let's talk about the next method. Okay? Here we go. Now, steps 1 through 3 are the same. So I'll say steps 1 through 3 are the same. Okay? So step 1 being factor the denominator. Sorry for burping. Here's Step 1. Factor your denominator. This is x plus 1, x minus 1. Okay? That's your denominator. Equals. Set up your partial fractions. A over x plus 1 plus b over x minus 1. Again, we have two linear factors here, x plus 1 and x minus 1. So one of the denominators needs to be x plus 1, one of the denominators need to be x minus 1. We just need to figure out what constants are on top. Okay. Now, step 3 is to multiply by the LCD. So the LCD is x plus 1, x minus 1. So we're going to multiply this entire equation times x plus 1, x minus 1. Okay? And so step 3, when we do this, again, notice this term. You're going to multiply it times this. So x plus 1s are going to cancel, and x minus 1s are going to cancel. So I'm left with x minus 5 equals, and then I'm going to take this term, multiply by the LCD here. X plus 1 and x plus 1 cancel, and I'm left with x minus 1 on top. So it's a times x minus 1 plus, and then again, b over x minus 1 times this. The x minus 1s cancel. I'm left with b times x plus 1. So this is b times x plus 1. Okay. Now this is where step 4 diverges. Okay? Step 4. Step 4 is to expand the equation and rewrite in standard form. I'll say standard polynomial form. You know, I've always had a gripe here. This is time for Mr. Spake to rant. Okay, are you ready? In Algebra 1, we tell you that ax plus by equals c is standard form for a linear equation, which is true. And we tell you that y equals mx plus b is called slope-intercept form, which, okay, fine. But standard form for a quadratic is y equals ax squared plus bx plus c. Standard form for a cubic is ax cubed plus bx squared plus cx plus d. And then for power of 4, it would be ax to the 4, bx cubed, cx squared, dx plus e, right? So then naturally, the standard form of a linear should be ax plus b. And that's actually what your calculator says when you run a regression. So I just don't know why we call this standard form. I think that's stupid, because that is standard form. But I guess really, I don't know. I don't know who made up this stuff, these terms. I'm fine with slope-intercept form being called that, but it's also standard form, I think. I don't know. Whatever. So here we go. Let's rewrite this in standard form by expanding. So I've got x minus 5 equals, distribute your a here, okay? This is ax minus a. Then distribute your b plus bx plus b. Now, I'm going to kind of group this together visually so to help you see. It's my x term and then my constant, right? And by the way, the coefficient on x is 1 times x. That's going to be important in a second. Equals, this is ax plus bx. Notice I'm putting the x's together. And then minus a plus b. Okay? Notice, these are our linear terms. And these, oh my God, that is a terrible little curly bracket. Woo! Okay, whatever, are our constants. Okay? So, if I factor out your x, right? So this is 1 times x minus 5 equals, factor out x, a plus b times x. And as I've written x to the right rather than x to the left, but you can write it either way, it's fine. And then plus, your constants are negative a plus b. Now, I want you to notice the comparison we're making here. 1 times x is equivalent to a plus b times x. Similarly, negative 5 is equivalent to plus negative a plus b. So you see we have two equations here. we can create a system. The coefficients on x must be equal. Therefore, a plus b equals 1. And the constants should be equal. So negative a plus b equals negative 5. Yeah? And so that is a system of equations. Let me lasso that a little bit. Whew. Let's move that to the side right here. That's our system, our 2x2 system of equations. And now that you have constructed a system of equations, you can solve for a and b. Now this one's pretty easy. We can just use simple substitution. Okay, so I'll add I said substitution, I meant elimination. If you add these together, a plus negative a is 0, plus 2b equals negative 4. Therefore, b equals negative 2. Now if you use substitution, like so, if a plus b equals 1, plugging in negative 2 for b, we find that a equals 3. Okay? And so, our final answer, right? Final answer. We took x minus 5 over x squared minus 1, and we decomposed that into a over x plus 1. That's 3 over x plus 1. 3 over x plus 1. Plus, this is negative 2 over x minus 1. So maybe I'll actually write that as minus rather than plus. So minus 2 over x minus 1. Boom. And that is that's method 2 using a system of equations. Okay? All right. I know it might seem a little bit more complicated, but it's really not that bad. I know that students seem to prefer method 1. And hey, look, that's the one I do. I think it's a little bit faster sometimes, but depending on the type of problem, this can be a very, very useful method. And I think this line of thinking, looking at the coefficients like this, really builds your understanding of polynomials, that those coefficients have to be the same. Okay, and that's method 2, using systems. Now, as far as the test goes, test and quiz, pick either method. I don't care, okay? Not me, not right now, okay? I just care right now that you are learning how to do this. And so that when you do get to pre-cal, when you do get to calculus, it'll be much easier to build your knowledge and learn the other techniques because you'll already have this basis down. I would recommend practicing both methods. Get comfortable with both because you never know. Maybe there might be instances where you think a particular method is more useful. Okay, now we would be done with the video, but we have a third example to talk about. And we've covered both methods, but we need to talk about repeated linear factors. Now, repeated linear factors, it's actually not that bad. Suppose I have, let's say this is x over x plus 2 cubed. Okay? That's not example 3, but I just want to show you how this is going to decompose. So a repeated linear factor means you have the same linear factor multiple times. You see, x plus 2 cubed is x plus 2 times itself. There's 3 of them. Right? So x plus 2, x plus 2, x plus 2. So the way this decomposes is you need a denominator x plus 2 cubed, but it is possible that one of the denominators has only 2 of those factors and not all 3. You see what I mean? Right? This one has all 3, but this one only has x plus 2 and x plus 2. And that could be a part of the fractions that add, because we don't know, right? We don't know. We know that the x plus 2 cubed has to be there. That's true. That's for sure there. But are there factors of lower degree in our denominator going forth, right? So we might say a over x plus 2 cubed plus b over x plus 2 squared plus c over x plus 2 to the 1. And so the way this works, whenever you have repeated linear factors, is you just got to cover all the powers, starting from the highest going down to 1, okay? So if I made this a 4, then I need to add another d over x plus 2 to the power of 4, okay? You got to make sure you have all of them. And that's how you deal with repeated factors. When you do get to quadratics in pre-cal, it is the same thing. That's the exact same idea. That just looks a little bit different because it's quadratic. But for repeated factors, you need to have every power descending, right, from highest to 1. Okay? Okay. So that's kind of how that decomposes. And look, some of them, you may find that one of your constants is 0, that you didn't even need to decompose that piece, but you don't know if it's a part of the composition. Okay, so steps are all pretty much the same. Let's factor the denominator. You're welcome to try and factor the numerator, but you don't really need to do that unless you're looking to simplify, perhaps. Maybe you can simplify. Notice that if I pull out the GCF x, then I got x squared minus 4x plus 4. And now I want you to notice that x squared minus 4x plus 4, that's actually, that is a perfect square trinomial, x minus 2 quantity squared. Now, if you need to do that, you can do your little cross. So you can say 4 is equal to 4, is equal to 2, right? And you can do all that business. But hopefully by now you're trying to recognize perfect square trinomials when they pop up. Okay? And so that is factored form. So then how do we decompose this, right? You know what? Let me write it on the next line. X squared minus 5x plus 8 over x times x minus 2 squared. Well, the first linear factor is x, so I know I need a over x. Plus, the second factor is x minus 2 squared, so it's b over x minus 2 squared. But you could have another partial fraction that only had the denominator x minus 2. Okay? We don't know. We have to see whether that's actually there. It might be. Okay? And there you go. So, let us add these together. Let's figure out what A, B, and C are. And I'm going to show you both methods here, just so you can fully see it. So, we need to multiply by the LCD times x minus 2 squared. Now again, this denominator completely cancels out with your LCD, so I'm left with x squared minus 5x plus 8 equals, now you do a over x times this, the x's cancel, and I'm left with a times x minus 2 squared plus, again, b over this times this, the x minus 2 squared terms cancel, and I'm left with just bx plus, and now this one might be the tricky one, c over x minus 2. So this is x times x minus 2 times x minus 2. So only one of them cancels. I still have this multiplying to c. So it's cx times x minus 2. Okay? And now I'm going to use either method. So I'm going to split this up. I'm going to do zeroing out. And I'm going to do systems. Okay? I don't care which way you choose. I don't. Okay? here we go, zeroing out. And this is the way Mr. Spake would normally do it. So pick zeros for each factor. Suppose x equals 2. Then I find plugging 2 in here. That's 2 squared minus 5 times 2 plus 8. That's 4 minus 10 plus 8. That's negative 6 plus 8. That's 2. So that's equal to 2. Equals. Now plug in 2 to this factor here. A times 2 minus 2 squared, that's a times 0 squared. That's gone, that's 0. So that's actually 0. We don't need that, 0. Plus, now bx, b times 2, right? So it's b times 2 for x. Plus, again, this is c times x is 2 times 2 minus 2. Well, that piece is 0, so that's c times 2 times 0, which is 0. That term is canceled as well. So that's plus 0. So since I have 2 equals 2b, therefore b equals 1. Okay? Now let's plug in another choice. Another smart choice would be x equals 0. And again, if you put 0 squared minus 5 times 0, that's nothing plus 8. So that's 8 equals, now do a times 0 minus 2 squared. That's a times negative 2 squared. That's a times 4. So that is 4a. Now b times 0 from this bx term, oops, this guy, b times x is 0, that's gone, so that's plus 0. And then c times x is 0 times 0 minus 2, well, who cares? That's also 0, plus 0. So since I have 8 equals 4a, that tells me therefore a is 2. Okay? Now you might find yourself in a predicament. You were able to cancel out this factor and this factor to find b. And you're able to cancel out this factor and this factor to find a. But if you wanted to find c, how could you cancel out both b and a? Well, both those options, they cancel out c, so you're stuck, right? So you say, well, Mr. Spake, how do I continue this? Well, if at this point you want to revert to systems, you could. You could substitute a and b and then expand and use systems. Or pick another value for x. Because you found a and b, you now know those values, right? So let's plug those in. Plug in a and b. Then I have x squared minus 5x plus 8 equals, this is a is 2, so it's 2 times x minus 2 squared plus 1x plus cx x minus 2. And now you want to figure out what c is. Well, if you want to figure out what c is, it's only one unknown. Just pick something for x. I'll say, just pick anything for x. By the way, that says for x exclamation point, not for x factorial. Haha. Okay, so I'll pick x equals 1 because 1 is easy to do math with. Looking at this term, 1 squared minus 5 times 1 plus 8. That's 1 minus 5 plus 8. That's negative 4 plus 8. That's 4. So that's 4 equals 2 times 1 minus 2 squared. That's 2 times negative 1 squared. That's 2 times positive 1. So that's 2 plus, well, this is just x. So x is 1, so plus 1 plus, and now this is c times 1 times 1 minus 2. That's c times 1 times negative 1. That's just negative c. So I'll say minus c. like so. So 4 equals 3 minus c. You can figure that out, right? Minus 3 from both sides. Negative 1 equals negative c. Therefore, c equals 1. Sorry. Is that right? No. 1 equals negative c. Therefore, c equals negative 1. Okay. And so, the decomposition, right? X squared minus 5x plus 8 over x cubed plus 4x squared plus 4x decomposes as a over x, that's 2 over x, plus b, that's 1 over x minus 2 squared, minus c is 1 over x plus 2. And that is our final answer. Okay. Whew. Did it. It's really not that bad. Okay. But you may have got stuck because you used the zeros to figure those things out. But how do you figure out the rest? Well, you just plug stuff in at that point. Okay. And if you get to even more complicated things, this gets a little bit messier, and you eventually have to start using systems anyway. So sometimes it is just better to use systems from the start. Okay, let's compare now using systems. I'll do this one in red. Okay. So we left off here. Okay. Now the strategy from here is to expand. Expand. So I have x squared minus 5x plus 8 equals, if you expand, I'm going to do my laser pointer here, a times x minus 2 squared. That's a times x minus 2 times x minus 2. That's a times x squared minus 4x plus 4. Okay? That's a times x squared minus 4x plus 4 plus bx plus cx times x minus 2. But we're not done expanding. Let's fully distribute all of this. Ax squared, I'm going to zoom in, minus 4ax plus 4a plus bx, and then let's distribute cx, so it's plus cx squared minus 2cx. Okay, now rearrange, okay, so that it kind of starts to look like standard form. Group all your x squareds. Ax squared plus cx squared. Okay, that's your x squared term. Okay. Then plus, I got negative 4ax plus bx minus 2cx. That's your linear term. And then plus 4a. That it? Yeah, plus 4a. So I want you to notice something. This is your quadratic term. This is your linear term. And this is your constant. See how it kind of looks like standard form? And now if you factor junk out, you say x squared minus 5x plus 8 equals a plus c times x squared plus negative 4a plus b minus 2c x plus, and then this is just some constant 4a, nothing to factor there. Okay? Now, and make sure this is a 1. Okay, that's 1 times. So let me use different colors to show you. 1x squared corresponds with a plus c x squared. Therefore, a plus c equals 1. Use another color. negative 5x corresponds with this thing, this other one. So then negative 4a plus b minus 2c equals negative 5. And then the last one, I don't know, purple, plus 8 equals 4a. So then 8 equals 4a. All right, well, let me just write that as 4a equals 8. Now, I do want you to notice we could solve this by hand pretty easy, okay? So this is your system. Can solve by hand easy with substitution. If you know that 4a equals 8, then a equals 8 divided by 4 is 2. Then a plus c equals 1 means that it's 2 plus c equals 1. So subtract 2 from both sides, so c equals negative 1. Okay? And then you have negative 4a plus b minus 2c equals negative 5. Well, that's negative 4 times 2 is negative 8 plus b minus 2 times negative 1, that's plus 2, equals negative 5. So it's b minus 6 equals negative 5, so b equals 1. And therefore, you got the same answer. Okay? So all of this copy. Same answer. Okay? There you go. And you know what I'm going to do? I'm going to lasso this. Can I shrink this? Resize. Look at that. I love this little iPad. Okay. And all I got to do is say 4b equals 1. Okay. Sorry, I'm just rearranging because I'm going to show you something else. I'm sorry for chewing up video time. Can solve easy. Solve with substitution. That's all the by hand business. So all of this is by hand. But if you had technology, with technology, use a matrix. Okay, so if you have access to a graphing calculator, that a matrix calculator that you can use, you can set up. Let's see. So this is A, B, C, right? Oops, and then constant. A, B, C, and then number. So then the first row is the coefficients 1, 0, 1, 1. Negative 4, 1, negative 2, negative 5, 4, 0, 0, 8. And then if you do RREF in your calculator, you'll find 1, 0, 0, 0, 1, 0, 0, 0, 1. And you'll get the same answer as we did, where A is 2, B is 1, and C is negative 1. So therefore, A equals 2, B equals 1, C equals negative 1. Okay? And there it is. Okay, that is everything fully worked out. I went slower than I did in class, and I explained a lot more, so maybe this is sufficient. I'm sorry, this video is probably really long, but I wanted to show you really both methods and how they're useful and how there's just so many ways you can go about doing this, okay? But again, just to hit home, you can use either the zeroing out method or the systems method. I don't care, okay? I do recommend practicing systems. I think it's a good idea. I think it'll really build your algebraic understanding of how to manipulate stuff, and will be beneficial to your long-term learning. But zeroing out is quick and efficient as well, and so I don't know. That's good too. So anyway, there's the video. Hope you enjoyed. Thanks for watching, and I'll see you later.